Hello everyone, welcome to this video. In this video, we are going to solve a question from December 2015 consisting of 3 marks. The question is, the resolvent kernel are xt lambda for the Volterra integral equation phi of x is equal to x plus lambda integration from a to x phi of s ds is which of these? So you need to suggest what is the resolvent kernel among these of the given Volterra equation, right? So now the question is, what is a resolvent kernel? What is a resolvent kernel? Yes. It is denoted by kernel, right? It is denoted by r xt lambda, that is, it is a function of xt and lambda, and it is calculated. It is a summation of m varies from 1 to infinity, an infinite sum of lambda raised to power m minus 1 and km xt, where what are these km xt? These are the iterated kernels. And how do one calculate these? These could be calculated by using the formula k of 1 xt, that would simply be kxt, that which would be given to us, and km xt, that would be integration from t to x k xz k m minus 1 zt dz, right? So this is the formula to calculate iterated kernels, and this is the formula to calculate the resolvent kernels. If you wanted to see how these things appear, you can watch the theory lectures, right? So as for now, let us get started. Let us first calculate the iterated kernels, and then we can use these kernels into this equation to calculate the resolvent, right? So in our question, what is k? Xt, that is given to be 1 in our question because there is no term, right? So this is 1, so ultimately k1 xt is equal to 1. So let us calculate k2 xt. What would be that? We'll use this equation. So integration from t to x, kxz, and then k1 zt dz. So this is equal to integration from t to x, 1 into dz. So that would be x minus t, right? So this is our k2 xt. Now let us calculate k3 xt. What would be that? It is integration from t to x, kxz, k2 zt dz, right? And this would be integration from t to x. The first term is equal to 1. The second term, this is equal to this. But the only difference is that we are taking the value of z and t. So it should be z minus t and dz. So this value is changed, right? So let us integrate this. It would be z minus t whole square upon 2. Limits of integration from t to x. So that would be x minus t whole square divided by 2. Right? So let us now calculate k4 xt. That would be integration from t to x, k of x comma z, k3 of z comma t dz. So that would be integration from t to x. This term is 1 multiplied by z minus t whole square divided by 2 dz. So that would be, ultimately this would be x minus t whole cube divided by 2 multiplied by 3, that would be 6, right? So x minus t cube divided by 6. This is our k4 xt, right? So you can proceed like this. So we cannot do this for infinitely many terms. So we'll stop here. We'll try to look and judge whether there is some similarity between these kernels or not. So let us have a look. Here the value is 1, here the value is x minus t, here the value is x minus t whole square by 2, here the value is x minus t whole cube divided by 6 factorial. You can write this as 3 factorial as well, you can write this as 2 factorial as well, you can write this as 1 factorial as well, right? So we can generalize this, so we'll get km xt, that would simply be x minus t raised to power m minus 1. Why? Because for k4 we have this power 3, for k3 we have this power as 2, for k2 we have this power as 1, and for k1 we can write this as x minus t raised to power 0 divided by 0 factorial, right? So this is true, divided by m minus 1 factorial. So we have generalized this term. This is our mth kernel. So let us put this value of iterated kernel into the equation of resolvent kernel. So our r x t lambda, what would be that? It is equal to summation m varies from 0 to infinity, right? Not from 0 to infinity, but from 1 to infinity. 1 to infinity, right? And it would be lambda raised to power m minus 1, because if we had used 0 over here, so we would have obtained lambda raised to power minus 1, which we cannot use, right? So it would be kmxt. So what is that? Summation m varies from 1 to infinity. Lambda in our question is lambda only, right? And so let me put the values. So it would be lambda raised to power m minus 1, and what is the value of kxt? It is equal to this. So x minus t raised to power m minus 1 divided by m minus 1 factorial, right? So we can open this term. For lambda is equal to 1, it would be simply we lambda raised to power 0, x minus t raised to power 0 divided by 0 factorial. So that would be simply be 1, plus then we have, when I put m is equal to 2, it would be 2 minus 1, so that would be 1. So lambda power 1, then x minus t raised to power 1. So it would be this divided by 1 factorial, that is 1, right? And then we have m is equal to 3, that would give me lambda square x minus t square divided by 2 square plus lambda cube x minus t cube divided by 3 factorial, and so on, right? So this could be written as e to the power of lambda x minus t, right? Why? Because we know the expansion for e to the power x, that is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial plus so on up to infinitely many terms. So this is our resolvent kernel. So let us look at our options. E to the power lambda x minus t is our solution, right? So option B is the correct option. I think you have understood how to solve questions related to resolvent kernels, how you can find this. Thanks for watching. I'll see you in the next video.